Welcome viewers. We know that an electric dipole is a pair of equal and opposite charges separated by small distance. Examples of dipoles are HCl molecule, water molecule, etc. We also know that a charge placed in external electric field experiences a force. Now, can you imagine what will happen if the dipole is placed in uniform electric field? In this program, we are going to discuss the behavior of permanent electric dipole in uniform electric field. Do you remember what a permanent electric dipole is? A permanent electric dipole is a dipole which has its own electric dipole moment, and this dipole moment is not induced by any electric field. Now, let us try to understand the behavior of an electric dipole by placing it in a uniform electric field. Let this is your dipole having charges minus q and plus q, and it is placed in a uniform electric field at any angle theta. Here this theta is the angle between electric dipole moment of the dipole, which is from negative to positive charge, and electric field. Suppose this is the center of the dipole and the length of the dipole is 2a. Now, as the charge placed in electric field experiences a force, therefore, the two charges minus q and plus q will experience force, and the force on minus q charge will be in a direction opposite to the direction of electric field, and it will be minus QE, and force on plus q charge will be in the direction of electric field, and its magnitude will be plus QE. Therefore, the net translatory force on the dipole will be plus QE minus QE is equal to 0. Hence, when an electric dipole is placed in a uniform electric field, it experiences a 0 net translatory force. Now, you can clearly observe that this minus QE and plus QE are two equal and opposite forces acting along different lines of action. Their lines of action are different, and because they are acting on different lines of action, so they will not cancel out each other. Instead, such forces constitute a torque or couple, and its magnitude is equal to, the magnitude of torque is given as force, magnitude of any of the force multiplied by perpendicular distance between the two anti-parallel forces, perpendicular distance between these two forces. Now, first let us find what is the perpendicular distance between these two forces. This is your perpendicular distance between the two forces. Suppose minus q is present at point A and plus q is present at B. So, the perpendicular distance between two anti-parallel forces will be this Bn, and we can find Bn if this angle is theta. So, we can find this will also be theta, and the Bn upon the length of the dipole, that is AB, is equal to sin theta, and Bn is equal to AB sin theta, and this AB is 2a, which is the length of dipole. So, the perpendicular distance becomes 2a sin theta. By putting values of the force, the magnitude of each force was QE, and the perpendicular distance between the two anti-parallel forces, we get torque is equal to this one, and we know that this Q into 2A. What is Q into 2A? It is called electric dipole moment, and it is denoted by vector P. It is E and it is sin theta. So, this is your final expression for torque acting on electric dipole in uniform electric field. Hence, we observe that when electric dipole is placed in uniform electric field, the net force on the dipole is 0, but net torque is non-zero, and torque is Pe sin theta. And this torque can be written as, in vector form, we can write it as torque is equal to P cross E. And from the rule of vectors, we know that cross product of two vectors is another vector which is perpendicular to both the vectors. Hence, this torque is perpendicular to P and this torque is perpendicular to E as well. And the direction of cross product can be easily found out using Fleming's left hand rule or screw rule. So, by putting a screw here, you can rotate the screw from the vector P to vector E through smaller angle. The direction of vector P is this one and the direction of vector E is this one. So, if this angle is theta and if I rotate the screw from vector P to vector E through smaller angle, we get that the direction of the torque will be normal to the plane of the paper coming out of it. It will be in outward direction. So, using screw rule you can find the direction of torque also. Now, let us consider three simple situations. Number 1, when the dipole moment vector P is parallel to E, that is electric field. It means theta will be 0. So, what will be the torque in this case? Torque will be P E sin 0, and we know that sin 0 is 0. So, torque will be 0. Number 2, when electric dipole moment vector P is anti-parallel to electric field, that is theta is equal to 180 degree. So, the magnitude of torque in this case will be P E sin 180 degree, and we know that sin 180 is also 0. So, again torque will be 0. So, when dipole is placed in uniform electric field either parallel to E or anti-parallel to E, the torque acting on the dipole is 0. Now, let us see the third condition, when dipole is placed perpendicular to electric field. P is perpendicular to E, that means theta is 90 degree. So, what will be the torque in this case? Torque will be P E sin 90, and sin 90 degree is 1. So, we get P into E, which is the maximum value. Hence, we can observe that an electric dipole experiences maximum torque when it is placed perpendicular to electric field. Can you depict the orientation of dipole in these three situations? Now, see what happens if the field is non-uniform. In that case, the net force will evidently be non-zero. Let us explain it with the help of a diagram. Suppose this is our electric dipole and it is placed in non-uniform electric field which is increasing from left to right. This is your electric field increasing field. Suppose the electric field at the position of minus q is E1. So, the force on this minus q charge will be towards left and it will be minus q E1. And suppose the electric field at this position of plus q is E2. So, the force on plus q charge will be towards right and it will be plus q E2. So, because we are going in the direction of increasing field, field is more at E2, that E2 is greater than E1. So, QE2 is greater than QE1. Hence, the dipole will experience a net force in the direction of increasing field. So, the net force will be QE2 minus QE1. So, we observe that when a dipole is placed parallel to the direction of field, then it experiences a net force in the direction of increasing field. Similarly, when P is anti-parallel to E, the net force on the dipole is in the direction of decreasing field. In either case, the net torque is 0, but there is a net force on the dipole if E is non-uniform. In general, the force depends on the orientation of the dipole moment vector P with respect to electric field E. Now, can you tell why does a comb run through dry hair attracts small pieces of paper? Let us discuss a simple problem based on behavior of electric dipole placed in uniform electric field. And problem is, an electric dipole with dipole moment 4 into 10 to the power minus 9 coulomb meter is aligned at 30 degree with the direction of electric field. So, theta is 30 degree and the magnitude of electric field is 5 into 10 to the power 4 Newton per coulomb, and you have to calculate the magnitude of the torque acting on the dipole. So, values of dipole moment, angle theta and electric field are given, and you have to find the torque on the dipole, and we know that torque acting on the dipole is given by the formula P E sin theta, and by putting the values of the P is 4 into 10 to the power minus 9, value of electric field is 5 into 10 to the power 4 multiplied by sin 30 degree, and sin 30 is 1 by 2. So, we get 2 to the 4, 5 to the 10, 10 to the power minus 9 multiplied by 10 to the power 5, that is 10 to the power minus 4 Newton meter. This is your torque acting on the electric dipole which is placed in uniform electric field. In this program, we discussed the behavior of electric dipole in uniform electric field. We found that a dipole placed in uniform electric field experiences 0 net translatory force, but a torque acts on it which always tends to align the dipole with the field direction. Further, we learned that in non-uniform electric field, dipole experiences non-zero net force as well as non-zero net torque. Thank you.